assignment, we are familiar with finding the muscle stresses and the joint reaction forces, even the ligamental forces. So here, I mean, one of the drawbacks which we came across was the assumptions actually. I mean, can anyone point out the main assumptions which we used during the calculations? I mean, most of the students missed it while answering during the assignment. But can anyone quote it? The assignment, sorry, assumption in the problem, elbow joint problem while finding the stress.
All the
Hello.
muscles are
Meaning
equal
muscles is zero.
stresses. So the sigma is same for all of them.
Means stress is same. Hmm.
Yeah, yeah. All the muscles are.
At the
Yeah,
same
you
mean
may say.
stress level.
Yeah, I mean, the stress is same
There's a
throughout. I
there's a
mean, for every
network
muscle.
issue.
Okay, can you hear me? Like, is it from my end or hello? I mean, you can see the screen, no?
Yes, we can see you and we
Yes,
can
sir.
hear you well.
Yes.
Everything is fine from my end, isn't it?
Yes, it's fine.
Yeah.
Okay, okay. So that was the main assumption. I mean, we are assuming that every muscle is it is stressed in the same. I mean, the stress generated in every muscle is same. That's what the assumption was, sigma m. So that was one of the reasons why I reduced marks for many of the students. I mean, the assumptions are very important while you I mean write the solution for these kind of problems, because unless and until you write that assumption, it's not clear. Like those things has to be mentioned, because similar problems will be there for the midsem examination. One of the drawbacks in most of the answer scripts was the lack of assumptions. So let's start our discussion on static optimization. So as we know, how do we find the muscle forces? Just tell me, like considering the static equilibrium, we use the equilibrium equations, isn't it, to find the muscle forces? We use the moment about a joint center, and we use the what we call force equilibrium equations. But the thing is, just consider if that assumption was not there, what would have been the outcome? Can anyone answer? If there is no assumption that the stress is not same throughout, like sigma m, there is no such thing as sigma m. So what will happen?
Multiple solutions for muscle forces.
Yeah. So there will be more unknowns than the available equation, isn't it?
Yes, sir.
Yes, sir.
Okay. So we actually suppress the more like this. I mean, we actually simplified the equation so that we can find the unknown using the equilibrium equations itself. But in the static optimization, we are not going to take such assumptions. Hmm? Clear? Hello. Can you hear me?
Yes, clear.
Yes.
Okay. Okay. So in static optimization, we are not going to take such assumptions. Rather than we will directly go with the equations, but in a different approach. So in the first slide, the same thing which is being explained here. Individual muscle forces are difficult to measure accurately, and there is no practical way to estimate muscle forces for the whole or even a part of the system, such as upper or lower limb. So mathematical model is necessary to predict it, and these are just the same things. And dynamic forces are then considered as static in every time instant. So it's more like a we consider that as a static problem and we solve it, even though it is dynamic. Like I mean, whole body moves in a dynamic way, no? Like even we flex or extend our hand, it's a dynamic motion. Like we take a particular instant and consider it as a more like a uh, pseudo static problem. So here it's a schematic overview of the static optimization procedure. As we know, inverse dynamics has got the inputs such as joint kinematics, and we get the joint torques as the output. And here we know, like, this is more equivalent to the elbow problem which we do, and the output will also will produce incorrect muscle forces. But what and this box signifies the static optimization. So here you can see an optimization problem. Okay, can you see an optimization problem here? Hello.
Yes, sir.
Yeah, so can you just note, can you just tell me what these are, these things? Optimization has got these elements, no? Elements of optimization problem, like cost function or objective function, something like that. Can you just tell me what they are, the elements of optimization problem?
So
Sir,
JFMT is the cost function,
Mm-hmm.
and the rest are constraints, sir.
Constraints or something else?
constraints.
Okay, constraints. Anything else, like there is, which is
So
the
second equation transforms muscle forces to joint torques.
okay. What about which is the design variable?
F of MT.
Okay, what is it? Like, can you just guess what FFMT is? It's there in the figure itself. What is
Muscle
FFMT?
forces.
Yes, muscle forces. So we are actually optimizing the muscle forces. So for the optimization, uh, the thing is, optimization can be done in several ways. Okay, so there are optimization schemes in which you need an initial guess. So can you name some optimization methods in which you have to give an initial guess to come up with an final answer? It has to be some iteration technique, no? So can you just name some iteration techniques in which you need initial guess, so that we can initiate the uh, what you call procedure? And there are a lot of iteration techniques now.
Gradient
Can you just name?
Simplex method.
Mm-hmm.
So we have
Simplex
method. solver
gradient
method,
descent.
Okay.
Newton-Raphson, Gauss-Seidel.
Okay, yeah, that's good, that's good. So those are, that's why we have this muscle force over here, and muscle forces and joint torques are the inputs of, general static optimization problem, and we get an optimized muscle force over here, and it's more like a feedback loop. So we update the muscle force according to the output of the optimization problem. So is it clear, this schematic overview? Is it clear?
Yes, sir. Yes, sir, it's clear.
Yes, it's clear now. So we have the design variables, we have the constraint equations, everything over here. So accordingly, and depending on the problem we solve it, there are several optimization techniques. So some of the optimization techniques require initial guess, some may not require initial guess. So can you just name one method in which we need not use any initial guess?
Lagrangian multipliers.
Yeah, yeah, correct. So let's go to the next slide. So here you can see, any equilibrium equation, whether it be force or moment, as a set, we can write those equilibrium equation in the form of Ax equal to B. Is it clear? One second, I am getting a call.
I couldn't
One second, one
understand
second.
the. I have
Excuse
one
me,
doubt
excuse me.
actually.
Hello, sir.
Hello.
Okay, one second. Give me a minute. Okay, sir. I think students are able to. Yeah. I think you turn off the video, then you will be able to get better connect. Yeah. Okay, sir. Okay, thank you. Okay, sir. Okay. Everyone can hear, no? Like, Professor told that he can't hear.
Sir,
It's clear, no? Like if
His
anyone
screen
is
is flickering a lot.
screen is flickering or anything else.
Sir, for us
Sir,
it's fine for me.
sir, some
It's
connectivity issue
fine
is
for
there,
us.
I guess. The voice is breaking at times.
Okay,
It's clear from here,
For us
sir.
it's not
but
clear. For us it's not.
I think I my connectivity is fine, I guess.
Yes, sir, your connectivity is fine.
Yes, it's clear for us.
Okay, fine. Okay, so yeah, so this force and moment equilibrium equations can be written in the form of a system of equations Ax equal to b, where x is the unknown muscle forces. So you can imagine like just consider sigma fx is equal to 0. So you can write a equation that is the first equation of the system of equation, then sigma fy equal to 0, then sigma m equal to 0. So so I mean, depending on you, like depending on the necessary, you can make a single equation or a three by three what you call set of equation using the force as well as the moment equations. Or if it is a 3D, then more equations will come into picture since we have more degree of freedom. So that's up to the model, like whether it is 2D or 3D. So this A will be the coefficient matrix, X is the unknown muscle forces, B is the right hand side of the equation, and that is obviously 0 since it is static equilibrium. So it's clear, no? This set of equilibrium equation writing in the form of system of equations. So it's not a new thing over here. So why do we need optimization? That I already discussed, because since it is an underdetermined system, means there are more unknowns than the equation. So we need just you can take the case of elbow joint problem where we have got more unknowns than the equations. So either we will have to take assumptions such as sigma m, like same stress throughout, or we have to do optimization analysis. So here, optimal solution of a system is an admissible solution x of minimum cost where a suitable cost c of x can be chosen. I mean, like it's a minimization problem to make it into simple words. So as the muscles can only generate positive forces, I mean, you know that muscles act in tension only. They don't act in compression. And for that also we have to use the necessary constraints. I mean, it's up to us. Like if we, I mean, it's a mathematical problem. So if at all we get negative, like it depends on the problem whether the it is stated whether the muscles can generate positive forces or not. So if it is not stated, then you need not use that constraint. If it is stated, then you will have to use that that muscle force is greater than or equal to 0. So you can see c of x is the cost function of unknowns, that is unknowns is muscle forces or stresses. H of x states a set of equilibrium constraint, g of x is inequality constraints. So that is clear, no? This optimization is just optimization problem, like telling you what it is. Can I hear someone? Like, is it audible?
Yes, it's audible.
Yes, sir.
Okay, okay, fine. So how many are there currently in the? Okay, 120. Yeah. So so whatever was I? Yeah. Yeah, cost equation, that is c of x. So using Lagrange multiplier, how do we tackle it? Can anyone tell? How do we tackle the optimization problem using Lagrange multiplier?
Yes, sir. Hello.
Yes, 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 I can hear.
So, right, initially we have to use the main optimization function
Mm-hmm.
that minus some Lagrange multiplier lambda times the constraint, equality constraint.
Okay, yeah,
So
that is
here
correct.
we'll having the main x variable vector, I mean
Mm-hmm.
the design variable, and then lambda as
Mm-hmm.
another variable.
Yeah, yeah.
Taking partial derivatives with respect to that x vector and lambda, we get any equations
Mm-hmm.
like n plus
Yeah,
1
yeah.
you need to solve.
That is perfect. So as he already said, so we are using a set of Lagrange multiplier. So so here x minus b is the equality constraint. X equal to b becomes x minus b equal to 0. So we have to implement that constraint. That is the main objective. So in order to implement that constraint into the objective function, we use a more like a variable, sorry, not variable, more like a constant, that is called Lagrange multiplier. And if we are using more than one equation, we will have more than one Lagrange multiplier. So here in the upcoming problem, we will be only using a single equation, that is that you will come to know. So we are actually converting the constraint minimization C of x into an unconstrained minimization, that is C of x plus the Lagrange multiplier into the equality constraint. So you consider if there is a constraint that muscle forces has to be positive or non-negative. So we will have to use another Lagrange multiplier set along with the what you call muscle force, because just consider muscle forces are g of x. So g of x, I mean, as it is here, I mean, just consider it is greater than or equal to 0. Then g of x is greater than or equal to 0. Then we will have to, in order to incorporate this into the cost function or the objective function, we will have to use Lagrange multiplier. So Lagrange multiplier's function is to convert the constrained minimization problem to an unconstrained minimization. So once we get this function, then we will not look into the inequality or equality constraints, because this is what we will operate with. So let's get into a sample problem. Am I audible?
Yes.
Yes, sir. Yes, sir.
Okay. So here I will just give you a hint. Okay, this, I mean, one problem will be there from static optimization. So everyone be alert, like I mean, for every steps there will be marks, so you know where you have lacked now. Like in the previous assignments, many have like ignored the assumptions and steps, some have just directly given the answers. So you have to write, if you have considered static equilibrium, then you will have to take, you have to mention like considering static equilibrium, or taking the moment about the joint center. But many have written these things, but some have not written. The thing is, if you don't write, then like it's more like you're not confident with your answer. So make the answer complete and perfect, then there will be enough time. So if you practice these problems, you will be able to answer it in maximum 20 minutes, because you are already familiar with what the steps are, everything. So be sure, make sure that you write every assumptions properly, every equations properly, and try to keep the final answers in boxes, so that it will be easier for us to check also. Like, I mean, if it becomes easy for us to check, then it will be like I mean, we will all feel good too. Like there will be this kind of a positive energy. Like, yeah, you are confident. I mean, if you are confident, you will surely try to I mean, make the answers more beautiful, no? So that's what I think. So just try to incorporate that in the coming exams. So I will consider this problem here. It's given that it is a two link segment and three forces are spanning. So F3, F2, F1 are the forces, G is the weight, P is some external force. So I mean, we are not talking any muscle or anything. We are just talking about three unknown forces. And as we know, uh, we are going to use the optimization problem over here. So here I'm going to use the moment about the center. Moment about the joint center, that is this point. I'm going to take moment about that particular joint center. Okay, So here it is said the forces F1, F2, F3 are the unknown, and they are called as X. I mean AX here, and must be chosen in such a way that it carries the forces P and G. So it just creates an opposite moment, but F3 is not causing an opposite moment. F2 and F1 will be balancing it. Only one equilibrium equation can be formulated for the unknown. So the system is redundant and unknowns can be optimally chosen. So here, one more thing is D1, D2, D3 are the moment arms about the joint center. Am I clear to everyone? Hello.
Yes, sir.
Okay, so moment arms uh, mentioned over here. D1, D2, D3 are the moment arms of the muscle forces. F1, F2, F3 about the particular joint center. And P and G are having the moment arms, which is equal to L sine Q and 2L cos Q. So from the diagram you can see 2L cos Q is the moment arm of T and L sine Q is the moment arm of G. So from the moment equation you can write F1 D1 plus F2 D2 minus F3 D3 is equal to G L sine Q minus 2 PL cos Q. So that is clear, no? So we are just writing the moment equilibrium in the form of Ax minus B. And can anyone tell me what is the objective function here? Like as a guess, like objective function will be a function of. I'm not asking you the direct I mean, what the objective function is. What will it be? It is a function of what? The objective function.
F1, F2, F3.
Yeah, unknown muscle forces. So it will be the function of unknown muscle forces. So here, uh, either it can be forces or stresses. So it need not be forces or forces always. It can be the muscle stresses too. Okay. So here we are taking the sum of the squares of the muscle forces. And this is the cost function. So we incorporate the equality constraint using a Lagrange multiplier by multiplying it with the Lagrange multiplier. That is nu here, nu into A1 sigma 1. Here A1, A2, A3 are the physiological cross-section areas. So actually we are just multiplying A into sigma equal to, that is F, no? A sigma equal to F, that's what it is. So we are using the same equation, AX minus B. As you can see, AX, that is here, minus B. The minus becomes
So
plus.
can you just tell the thinking behind the C, how the cost
Yeah,
function?
that is actually criterias. I mean, objective criterias, function criterias. I mean, I'll discuss the different objective criterias we can follow
So
because
is it like fixed or there is some rationale behind it?
there is because either the two, I mean, the most common approaches are we are taking muscle forces or the muscle stresses. So as I told you, like we have to find the muscle forces, but the thing is the muscle forces, the area of cross section is different for different muscles. Okay, so what it is, we are actually not incorporating that variation of area, that difference in area, in the muscles. Are you getting me? So here we are actually taking this A1, A2, A3 constants over here. But actually what the researchers have found is you can either use the forces or stressors. It doesn't make much of a difference. Are you clear? Is it clear?
Yes.
Why is it
So
square? Sum of square.
some of sum of squares, I mean the minimization, I mean it's more like minimization of the squares. I mean there are other criterias and then I will discuss it there. Okay, don't worry about it. Like we can take you're asking me whether we can take cubes or quadrature, isn't it? That's what your question is, isn't it?
Can you hear me, Sevi?
Yes,
Can you
yes, yes,
hear
I
me?
can. Yes.
But I cannot see anybody. Somehow my connection is not that good. Uh, the thing is that
Yeah.
the muscles are soft tissue. Can everybody hear?
Yes,
Yes,
sir.
sir. Yes.
Yeah. The muscles are soft tissue. They can stretch, okay, much more than the bone. Like bone is more rigid, but muscle, soft tissue ligaments tend uh, more than sort of any solid. What happens when a material is generally flexible, more stretched, it can be more stretched. The stresses inside that material is generally less. Okay, you get my point. So muscles can get stretched very easily, but stressed less. The stress is basically the stresses inside the muscle bundle is the force divided by the physiological cross-sectional area. So what happens is they try to minimize the square of the stresses. So when you actually square a term, that means if if the value, if there is, because we are doing a uh, numerical procedure, so if there is an error, that error is also squared. You get my point? Hello?
So sigma 1, sigma 2, sigma 3, like are the principal stress components of like at which point are we calculating them?
No, no, no.
It's
I
not,
mean,
it
there
is
is
not
nothing to do
principal
with
stress.
the principle. Yeah.
It's nothing
I
to do
mean,
with
they are
principal
just
stress.
muscle stresses. I mean,
Muscle
there
stresses.
are there are criterias in which we use even the moments. I mean, moments as well as muscle forces. So you need not worry much about the objective function here. So there are other criterias. We have just chosen one of the several criterias. I will actually discuss a table of criterias. I mean, if you just go through
Yeah.
the last slide, so you will see several criterias as well as several methods. So you need not worry about.
Can you show
Yeah,
the
yeah, yeah,
last page,
yeah. I will.
Debbie? I cannot
Yes,
see
yes.
anything, by the way.
Okay, yeah. Here you can see we can take a square, cube, whatever it is, 4, 5, 6, any degrees over here as n. So this is xi is either muscle forces or stresses. Everyone can see now. Hello, isn't it? Can you
Yes.
see?
Yes.
Yes, we can see.
Yes.
Okay. Yeah, so there are like different criteria. So you don't have to worry about this particular criteria. Why we have taken square? Why we have taken stress? So we can take even the forces as well as the moment. So like many researchers have different approaches. So you need not
So
worry about that.
basically it is mini.
Yeah, minimization it is. Yeah, minimization of the muscle stresses or forces. That is the main thing. We are minimizing the muscle stresses as well as or the forces. Can I start? I mean, uh,
Uh,
can I
just one
proceed?
question, Sebi.
Yeah.
So we studied about instrumented prosthetics, right, which can measure forces inside the
Force,
body.
yes, force divided. So it's just a material, say it's uniaxial sort of thing. So you cut a section and basically the uniaxial stress, okay? And that stress is F, the force, normal force divided by the physiological cross-sectional area. So either you minimize the sum of the quadratic muscle forces or you minimize the sort of sum of the uh, muscle stresses, quadratic muscle stresses. They use the square term, of course. So any error is squared. So that is basically a mathematical procedure. So there is minimization of quadratic muscle forces, minimization of the sum of the quadratic basically sum. I missed the word sum. Minimization, first criteria can be minimization of the sum of the quadratic muscle forces. Second criteria can be minimization of the sum of the quadratic muscle stresses. Third criteria, minimization of the sum of the quadratic muscle forces normalized to the maximal muscle force. Okay. This way, there is another fourth criteria, minimization of the maximal muscle stress in the entire mechanism. So these sort of different optimization. Hello, can can anybody who is making this sound? Hello. Yeah. So many researchers have put forward several optimization criteria, but within that, different proposals, as Sebi said, that minimization of this sum of the quadratic muscle forces and minimization of the sum of the quadratic muscle stresses has been more popularly used by different researchers. Okay, Sebi, you can carry on then.
Yeah. So the objective function um, has been converted into an unconstrained function over here by incorporating the constraint equation along with the Lagrange multiplier. So we have got A1, A2, A3, which are the physiological cross-section areas, and sigma 1, sigma 2, sigma 3 are the muscle forces, which we are going to minimize. So as I already told, we are going to use the Lagrange multiplier, and one of the student mentioned that we will have to differentiate this function with respect to the muscle stresses as well as the Lagrange multiplier. That's what I have done here. It is differentiate with respect to sigma 1, sigma 2, sigma 3, and we got sigma 1 plus nu a1 d1 equal to 0, sigma 2 plus nu a1 a2 d2 equal to 0, sigma 3 plus nu a3 d3 equal to 0 by differentiating with respect to sigma 1 and sigma 2 and sigma 3. So from this, by just solving these three equations, we get an expression as, we just you can just look into it, like just multiply d2a2 to the first equation and d1a1 to the second equation, and you can eliminate this term consisting of Lagrange multiplier, and you will get this expression. Thereby, sigma 2 equal to d2a2 divided by d1a1 into sigma 1. And similarly, taking the second equation as well as the third equation, you can get this expression sigma 3 in the form of sigma 1. So what we will do is, next we will differentiate this function with respect to the Lagrange multiplier, and we got this sigma 1 plus sigma a1 d1 plus sigma 2 a2 d2 plus sigma 3 a3 d3 minus this momentum equal to 0. So next we are actually going to substitute this sigma 2 here, sigma 3 here, and we will get a solution for sigma 1. So we can see sigma 1 in terms of A1, so areas as well as the momentums and the external forces and their momentums. So that's over here. L is the length. 12 is the length of this particular link. So that's it, like sigma 1, sigma 2, sigma 3. The thing is, if you just practice it 1 or 2 times, you will be getting familiar. There is nothing big over here. It's not a big rocket science or something. It's just a Lagrange multiplier. We are just using Lagrange multiplier to find the sigma 1, sigma 2, sigma 3. But the thing is, in this particular problem, we haven't incorporated this constraint where muscle forces are non-negative. So in order to incorporate that, you will have to use more Lagrange multiplier, like for example, nu into that particular force. So if there are three forces, then you will have to use nu A FA plus nu B FB plus nu C FC. So three more Lagrange multiplier will come into picture since we are using three more constraints. Okay, three more inequality constraints. So that you will have to do by yourself. I mean, it's nothing more. You just have to use the same procedure. It's just incorporating a few more constraints, which will force the muscle forces to be non-negative. Is it clear? Anyone has got any doubt?
Sir,
Yes, yes.
sir, that non-negative constraint will include two more variables, right, for each equation. One Lagrangian multiplier and another slack variable.
Can you tell me once again?
Like all the before equations, the constraint equations were equality constraints, right? But now if
Yes.
you include a non-equal inequality constraint,
Uh-huh.
then we have to use two variables for a single equation, the Lagrange multiplier as well as a slack variable.
Yes, 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 yes. That is
And then
correct. Yeah, I
like we'll
mean
be
that's
having two more variables, right?
yes, yes. I mean that is more like an assignment. You have to look into it and you have to solve it. Okay. Maybe that is the when that may be a more like a assignment for you. Like otherwise you won't do something by yourself, no? Just use more Lagrange multiplier as well as variables and try to find out whether there is any change in the muscle stresses expression. You got it? So basically, you just have to look into the Lagrange multiplier method. Check whether any changes are there when you incorporate non-inequality or equality constraints. Is it clear, everyone?
Yes, sir.
Okay. So we discussed about the Lagrange multiplier method. So there are few other methods. Okay, Newton-Raphson and simplex method. I mean, those methods require initial guess. That's why I kept it to Lagrange multiplier method. So as I already mentioned, there are several optimization approaches which can be used to solve the redundant muscular force system. And these cost functions are sometimes called the performance criteria. And we can see here a typical performance function is a sum of the muscle stresses or forces raised to a power. So those are just stuffs, and here I have discussed about the I mean popular criterias as well as solution methods and the references to it. So if you are really interested, you can go through these papers. I have put it in the reference. So here X can be muscle forces or stresses, N can be 1, 2 or 3. M is the moment at all the joints included in the system, and M comes over here. So each system has got different approaches, and these are just approaches which has been quoted or used in some papers. Okay, so there is no such hard and fast rule that you have to use this approach itself. I just took one of the approaches which is quietly popular, and an easy method so that you will understand, that is Lagrange method, so that it's not much of a load on you. So if it is simplex or non-linear methods, then it will become a bit quite hard for you as well as me. I mean, to make you understand. So Lagrange method is quite easy method. So I mean, as I told you, you have to look into this Lagrange method, like non-constraint, sorry, no equality as well as non-equality constraints, how to change. Like Lagrange method is all about converting the unconstrained to the constraint to the unconstrained form. So that's over here, and I have just mentioned the references over here. So some of you students have approached me asking this marks regarding the second assignment. So as I already mentioned, like these assumptions are very important. So one should mention these assumptions, and always mention this. If you are using the equilibrium equation, always state that the static assuming the static equilibrium, the force equilibrium equations are, moment equilibrium equations are, and always try to mention, like if you are using some term other than which is mentioned in the equation, just say like D is the momentum, or sigma is the stress, or anything. Like make it clear and perfect, so that if it is clear and perfect, we will also feel that yeah, this is genuine. Like you haven't copied from anyone, so it shows your confidence. Okay. So is there any other query, like general query or anything? Hello.
I wanted to ask you whether it's possible to measure the muscle forces experimentally. So this is like a theoretical thing. We have taken many cost functions, different kind of cost functions to evaluate muscle forces. So if we can measure muscle forces experimentally, maybe we could model them and find an more accurate objective function.
No, I mean objective function. I mean the sole purpose of optimization is to find the muscle stresses now. So if it is possible experimentally, I'm not sure. Like, is it possible, sir? I don't think it is possible. I mean, how is it possible to measure the muscle stresses? I'm not sure about it, 100%, but I will look into it. I don't think it is sure. Yes, sir. I'm not sure whether he is online. Yeah, I can hear, sir. Sorry, I think you will have to turn off your video because audio is not. Yeah. 1 second, sir. Why are you muted? Have you muted yourself? Yeah.
No.
I think you have muted yourself, or is it some?
Unmute. I'm trying to unmute, but it doesn't.
No, you. Wait a minute. Wait a minute, sir. No. Okay. Can you unmute yourself and? Yeah. I think it's the network connection.
No,
I think it's the network connection. Can you turn off the video? I think it is the network connection, sir. Yeah. Okay, sir. Okay. Okay, sir. Okay. Okay, sir. Sir will join within few minutes. So I'm not sure about that, like whether you can measure it experimentally or not. That's why I wanted his opinion too. But from my knowledge, I don't think it is possible experimentally, because that's why we are using these methods to optimize and find the muscle forces as such.
And these methods are only for a static process, right? So we
Yeah,
cannot.
there are dynamic. Wait a minute. There are dynamic optimization schemes too. So we have only mentioned static optimization schemes here, but there are dynamic schemes, and I will quote one paper. This pseudo inverse algorithm. I think it is a dynamic. I mean, this Yamaguchi et al. If you go to that paper, then you will get to know more about this dynamic optimization scheme. I mean, I have shared it in that table, Yamaguchi et al. So a computational.
Can you hear me, student?
Yes.
Yeah. So it's a good question actually. Now, let me put off my video. Hello. Hello. Can you hear me?
Yes, sir. Yes, yes.
Okay.
Yes, sir.
So, very quick answer. This muscle force measurements, many attempts have been done with surface EMGs. Okay. So, during a physiological activity, they surface EMG measurement. EMG is a device, as you all know, signal. They try to directly measure muscle forces. Okay, muscle stress, no, because muscle stress can be calculated based on the physiological cross-sectional area of the muscle. Okay, so surface EMGs, but that is only, you can put that surface EMGs on a patient. You can stick these transducers on patient, and approximately you get some data, but not very precise. You get my point? Hello?
Sir, yes, sir.
So, if you look into sort of this muscle force measurement, you may get literature available, different attempts, and even in HIP 98, HIP 98, they also measured some, and the important thing is muscles are so difficult to sort of approach within a muscle. I mean, in an in vivo system, okay, in a living system, the muscles crisscrosses each other. You have several, it is so difficult to put the probe inside the muscle that can actually give you the data during a physiological activity. Okay, so it is very complex and very difficult to directly measure muscle forces. Okay, does that answer your question?
Yes, sir. Yes, sir.
So who asked this question? It's a good question anyway. Abhinav?
Yes, sir.
Abhinav, okay. Abhinav, if you like, you can look into these EMG measurements. Okay,
Yes, sir. I'll look into that.
or you may find these EMG measurements in the HIP 98 as well. But muscle
Okay, sir.
forces is always very difficult to directly measure because the system inherently is very difficult to probe. Okay.
Yes, sir.
Only there are some surface measurements, like as I said, with transducers uh, being stick on your skin. But again, there are there are definitely errors because the skin will move relative to the muscle. It is not always true that you are measuring actually the muscle forces, because the movement, the signal will have errors of movement of the skin implicitly. You get the point?
Yes, sir. I got it.
You can yourself feel that. Anyway, Sebi, you can carry on.
I mean, yeah, man. Is there any other doubts? I actually finished the PPT, so I can clear any doubts regarding the PPT, or I mean, if there is any query related to the marks of the assignment too.
Sir, I had a following question to what Abhinav was asking. So, sir, in these devices like the exoskeletons or the rehabilitation robotics or the robots, how do they decide the torque that the motor has to give at each joint? Because for that they would require accurate measurements of the muscle forces in the body, right? Or is there some other way to do
This
it?
is no. There is a gross difference in with exoskeleton and this aesthetics and what is lecture. Okay, so this is a living system. When you are designing prosthetics, you don't say you are replacing a leg. Okay, it is either below knee prosthesis or above knee prosthesis, prosthetics. Okay, which are purely external devices. Purely external devices. Did you get my point? So there
Yes,
is
sir.
no muscle. There is no muscle in a prosthetics.
Sir, but like if we are making a device to aid in walking, then the device basically, since our legs are not able to generate the required force, the device provides the excess force, right? That is required. But how do they calculate the excess if they don't know the actual value? So that was my doubt.
See, there are of course some standard values. Okay, when there is a host of data, like if you look into HIP 98, you will see the data varies, but there is a average value or a range of average values or range of values within which you can see that the muscle forces are like this, it stays like this sort of thing. So aiming, you can actually design a system trying to mimic that value. You get my point?
Oh, okay, sir. Yeah, okay.
So now for these things, you have first think first. So you first go and look into HIP 98. Okay. So for instance, in a walking, what, what is the, if I ask anybody, what is the maximum or hip contact force? So it is 2.38 times the body weight as per HIP 98. But it can vary. It can be 2.3 to 2.4, 2.45, but not more than that. Okay. Earlier researchers, they have found out something around 3 times body weight. But with advancement in technology, more precise measurements, better computational facility, this value of 3 times body weight, hip joint reaction force maximum, has come down to about 2.4 times body weight. Okay? So things should be around that. So you'll see the variation in the patient. You'll see 4 patients. Then they have averaged a value. There's a range of value like this.
Okay, so there is a maximum cap for all forces that is accounted. Like
Yeah.
they can't exceed a certain. Okay.
But see, there are, if you design a mechanical system which would mimic some movement, you always have some factor of safety. You get my point?
Yes, sir. Yeah.
That is inherently always in the system. Because if you look at a patient whose one leg has been amputated, this is very frequent for soldiers, the army, because they step into minefields and they lose one of their limbs. Okay, if not two, both of them. So when you see them walking with that prosthetic leg, there is, you can immediately recognize that it is not a perfect gate, and that shows up in the data. If their gate is measured through 3D motion capture system and with the data of the force platform, there is deviation, but the deviation is maybe within a minor range. So because it is so difficult to actually mimic the natural system, but still it gives them, some amount of relief, because they can at least walk. Otherwise they couldn't have, without the two legs you cannot walk, or it will be difficult to sit up properly, you need an aid. So they get back, definitely not 100, but certainly 80 to 90% life. Hello?
Okay, sir. Yeah, I understood, sir.
Yeah. I can give you an example in the campus. Perhaps you all know chemical engineering professor Sunanda Dasgupta. Chemical engineering professor, do you know Sunanda Dasgupta? Very senior professor. He was Dean Research earlier. So his one leg below knee, from ankle, has been amputated because of cancer. Okay, but his whole thing is done so nicely that it is difficult to recognize whether it's a natural leg or a natural ankle or an amputated one. He leads a normal. He drives. He does all work, stair climbing, everything. I know. I meet him quite often, and I know I was very worried during his illness when he was detected with malignancy. But in the it's a live case within the campus. Professor Das Gupta was amputated, and he is absolutely leading a normal life. But of course, his amputation is minimum, only in the sort of the ankle up to the ankle, the foot, basically. But if you do more amputation, like from the knee joint, the whole limb, the limb segment, the tibia part, the foot part, there are patients who are amputated from the hip itself. There is a stump from particularly many soldiers. This happens because once you step in a mine and then you lose your whole limb. Okay, so then it becomes more and more complex with the movements.
Okay, sir. Thank you.
Okay. Okay. So I leave the class here, and thank you, Sebi.
Yes, sir. Thank you.
Yeah, I have seen your PPT slides earlier, but at this moment I only could see a few because I have a problem with this connection. The students up to this class, whatever has been taught is in your syllabus for the major test 1. Okay? Did you get my message?
Yes, sir.
Yes, sir.
Okay, sir.
Okay. Up to the static optimization procedure for estimation of muscle forces, whatever we have taught, we will not teach anything extra, but we will, if you need, in the next Wednesday class, we can clarify things, but that will be based on HIP 98. I've been telling you, just get on with the HIP 98. Okay, you will learn a lot. Okay, so we can clarify doubts in HIP 98 and help you with the preparation, of your report, things like that. But Generally, this is where the first part of the course ends. Okay? And your major test 1 will be conducted based on the syllabus that we have taught you, all details up to today's class. Clear? Okay?
Yes, sir.
So anything else you would like to clarify with SEBI, you can go along. I will leave the meeting because there is a lot of problems in getting connectivity from here. Okay? Then thank you all and thank you for your nice lecture.
Okay, so thanks.
Thank you, sir.
Thank you.
Thank you.